In this video, we're going to be continuing the discussion of rate laws. In the previous video, we had covered differential rate laws. Now we're going to be looking at another form of rate laws, which are integrated rate laws, which shows how the concentration of a given species or a particular reactant, the concentration of a particular reactant in the reaction, depends on time and vice versa, or depends on time, since time here is typically considered to be the independent variable. So let's consider a first order reaction where the reactant A will yield products and the rate is equivalent to K times the rate is equal to the rate constant K times the concentration of A. This is what we considered last time to be the differential rate law. This is the differential rate law expression. So we want to note that if the concentration of A doubles, then the rate of consumption and rate of production would also double. Okay? So just keep this in mind. Alright? So it's important that we determine the uses for integrated rate laws to help us better understand why it's important to know about integrated rate laws. So there are two primary uses of integrated rate laws. The first is to determine the amount of reactant or product present after a given period of time. And the second use is to estimate the time required for a reaction to proceed to a certain extent. Okay? Another concept that we want to be familiar with is the half-life of a reaction. So the half-life of any given reaction is the amount of time required for 1/2 of a given amount of a reactant to be consumed. Okay, so let's say, for example, the reactant, there is 0.500 molar concentration of C6H4, or sorry, C2H6, right? And then we find that after a certain amount of time has passed, we find that half of this concentration is left, right, in the reaction. So C2H6, right? This is the time between these two concentrations is what we consider to be the half-life, T1/2. Okay. So with this in mind, with these concepts in mind, I think it would be best to go through the various forms of integrated rate laws, starting with the integrated first order rate laws. So for a given first order reaction where rate is equal to K times the concentration of A, note that this is the differential rate expression. The integration of this function, or the integration of this rate law, the integration of K times the initial times the concentration of A, will give you the concentration of A at any given time T, which is equivalent to the initial concentration times e to the power of negative kt. So let's just describe the meaning of these symbols. So the concentration of A under script T refers to the concentration of A at any given time of T. A0, the concentration of A0 is what we refer to as the initial concentration of A, and K is equal to the first order rate constant. Okay. So there are two forms of first order integrated rate laws that we need to know. So the first form is the natural logarithm of concentration of A is equal to negative kt plus the natural logarithm times the natural logarithm of the initial concentration. So what are the important details here? So this formula here for the first order integrated rate law shows how the concentration of A depends on time, right? And if the initial concentration and the rate constant K is known, we can find the concentration of A at any time. Now, what we want to do with this formula usually is we want to plot the natural logarithm of the concentration of A against T. So the natural logarithm of the concentration of A is Y, and T is considered X, the independent variable. Okay. So when we plot the values obtained from experimental data from a first order reaction, we'll be able to get a straight line or a straight line or slope or a straight line where y equals mx plus b, right? Where the negative slope or negative m is equivalent to k, b or the y-intercept is equal to the natural logarithm of the initial concentration, and x is equal to time or t. Okay, so just remember that the key idea behind this form of the first order integrated rate law is that this form is used for graphs since it shows a linear dependence of concentration in time. Okay, and this is just a mathematical proof showing that this exists. So let's say, for example, we want to integrate the rate, and this is what we get as we've seen before, that this is the first order integrated rate law, right? What I did here is I essentially moved the initial concentration to the left side. I moved this here, right? That's what happened in this step. And then I applied the natural logarithm on both sides to cancel e, right? And then to isolate, to get the same formula, I essentially just applied the natural logarithm rule where ln b over c equals ln b minus ln c. That's essentially the rule that I applied here to get this, okay? Just for reference, you don't need to know this, but just if you want, if for your own interest, you can just take a screenshot of my math if you feel like it would help you understand the concept of first order integrated rate laws. Okay? With this in mind, let's go through an example. So using this form of first order integrated rate laws, okay? So we're given here graphical data, right? A first order rate law graphing the natural logarithm of the concentration of H2O2 against time. Okay, so this is the experimental data that's presented to us. Okay, so what we want to do is determine the rate constant, K. Okay, so let's remember first that this is my solution to the problem. So let's remember first that the negative slope or negative m equals k, and the natural logarithm of the concentration equals b. So as we can see here from experimental data, that the y-intercept here is 0.000. Okay, but we don't necessarily need to find the y-intercept here because what we're looking for is k, and what we need to find k, so this is my mistake, we don't really need this information here. So what we need to find k is determining what m is. So from basic pre-calculus, we know that the slope is equal to y2 minus y1 over x2 minus x1. So as you can see here, I've already determined the values of x2, x1, and y2 and y1, right? Plug in these values here, and you're left with plug in the values here and calculate the final answer. And what you're left with is a rate is the slope being equal to negative 0.116 per hour. Okay, because the units of time are presented in hours. So this is what m is equal to. So therefore, k equals negative slope, right? And the negative, so negative 1 times the slope, which is negative 0.116 per hour, is equal to 0.116 per hour. So this is what we call the rate constant. So just make sure that you keep this in mind, okay? Now, it's so important. This is a very important recurring theme here, is that when we plot these values on a graph here, we see that a linear relationship between the natural logarithm of the concentration of H2O2 and time, right? We know that this is a first order reaction because there is a linear correspondence, like there's a linear relationship formed between the two variables that serves as an indicator that this is a first order reaction. Okay, this is a very important detail that we need to know here. This is a very important feature that we need to know for when you're plotting values against time. Whatever form you plot it in, make sure that it gives a straight line to show that this is a positive indicator that indicates that this is a first, second, or zero order reaction, as you'll see later below. You'll see the recurring themes. Okay. Moving on to the second form of first order integrated rate laws. So the second form of first order integrated rate laws is expressed as a ratio, as opposed to the first form, which looks very similar to a regular plot where y equals mx plus b, right? And showing that linear dependence of concentration on time. This second form here is expressed as a ratio, right? Where the natural logarithm of the initial concentration over divided by the initial concentration at any given time is equivalent to negative kT. Or the other form of expressing this is the natural logarithm of the ratio between the concentration of A the ratio between the concentration of A at any given time over the initial concentration, which is equivalent to kT, both of which are very similar to the ratios that I explore here, right? So these forms are important because this form can be used to express direct or indirect proportionalities or ratios, right? And it's useful for solving equations that don't explicitly mention the concentrations of the reactant and only mention changes in concentrations. So this is a very important detail that we want to note here when we're using this form for first order integrated rate laws, is that we can use this form to solve questions that don't explicitly mention the concentrations, and rather only mention the changes in the concentration. So say, for example, at a time t, the concentration is reduced by 60%. So we apply this formula where the natural logarithm of the concentration at any given time t divided by the initial concentration is equivalent to negative kT. We recognize that the concentration of A T is equal to 40%, because this is what the concentration is at a given time, times the initial concentration. And from that, what we see here is that we can cancel out the initial concentrations in the expression, and what we're left with is the natural logarithm of 40% is equal to negative kt. Okay, so let's go through an example. So the rate constant for the first order decomposition of cyclobutane C4H8 at 500 degrees Celsius is 9.2 times 10 to the negative 3 per second. Okay, so let's keep this detail in mind. Right? How long will it take for 80% of a sample of C4H8 to decompose? So we know that K is equal to 9.2 times 10 to the negative 3 per second. We're looking for the time, right? So we want to apply the second form, given that we don't know what the initial concentration is, right? So we don't know this is, we don't know what this is. So we're left with missing information. So what we want to do is we want to isolate for t, which is what I show here. So I apply the formula, the natural logarithm of the concentration of A of a given time t over the initial concentration is equal to negative kt. We isolate for t by dividing both sides, right? And then we recognize that the concentration of a given time t is equal to the initial concentration times 20%, because that's what the concentration at a given time t, which is what we're looking for, t, right, is equal to the initial concentration times 20%, right? So only 20% of the initial concentration remains, and that's why we recognize it as the concentration of A at given time t, right? From there, we cancel out the values here, right, by applying this in the formula. And what we're left with is 1 over negative k times the natural logarithm of 0.2, or 20%, which is equal to t. You plug in values, and this is what you're left with. I round it to 2 significant figures here. 2 sig figs, right? Feel free to check my math to be sure that I'm correct, but I believe this is what the correct answer is. 1.7 times 10 to the power of 2 seconds. That's what t is. Okay? So let's go through the concept of half-life of first order rate laws. So remember that the half-life is the amount of a reaction is the amount of time required for half of a given amount of a reactant to be consumed. Okay? So we want to apply this ratio where the natural logarithm of the initial concentration over AT is equal to KT. So when T equals 1/2, the concentration of A at T of 1/2 is equal to 1/2 of the initial concentration, which makes sense because, as I said before, the half-life is the amount of time required for the amount of time required for half of a given amount of a reactant to be consumed, or that's left over, right, to be reduced to its to half of its initial amount, right? So it's very important that we recognize this. This is super, super important. Okay. Therefore, if t equals t 1/2, the natural logarithm, right, we want to continue isolating for t. So this is just the math proofs that show that in the end, the half-life of a first order integrated rate law is equal to ln 2 over k. Okay. So you can try to understand the math proofs here. I think it might be helpful, but use it at your own discretion if you need to. Okay? So, some important details. The half-life for first-order reactions depends solely on K. It is independent of the concentration of A. So, the half-life for first-order reactions remains constant, meaning that it does not change over time. So we can see here, based from this graph, that the half-life, that the length of the half-life remains constant. It does not change, right? So let's say, for example, the half-life is 7 seconds, right? So for the first 7 seconds, we find that 0.10 of a molar of a concentration of a reactant will be reduced to 0.05 after 7 seconds. And then after another 7 seconds, it'll be reduced to 0.25. Right? So this is on the third half-life. And we find that this will be 0.25 molar concentration afterwards. Okay? So let's go through an example of half-life for first-order reactions. So let's say, for example, we want to calculate the rate constant for the first-order decomposition of hydrogen peroxide, right? So there's a lot of experimental data here, but what's most important is we figure out the half-life, right? We find that it takes about 6 hours, or 2.16 times 10 to the 4 seconds, for the initial concentration to be reduced to half, where the initial concentration is 1.000 molar concentration at 0 seconds, but 2.16 times 10 to the 4 seconds later, the concentration will be reduced to 0.500 molar concentration. Okay? So, using this information, T of 1/2 equals ln 2 over K, which is equal to 2.16 times 10 to the power of 4 seconds. So therefore, K equals ln 2 over T, or over the half-life, which is equal to ln 2 divided by 2.16 times 10 to the 4 seconds, which is equivalent to 3.209 times 10 to the 5, which is equal to 3.21 times 10 to the power of 5 per second. This is what we show as the rate constant for this particular reaction. Moving on, we have integrated second-order rate laws. So for a given second-order reaction where the rate is equal to K times the concentration of A with a second reaction with a reaction order of 2, or to the power of 2. This is the differential rate expression here, right? The integration of this rate, right, will result in 1 over the concentration of A of T, which is equal to KT plus 1 over the initial concentration. So for this, you only need the initial concentration in K to find the concentration of A at time T. So some important details. This equation shows how the inverse of the concentration of A of a given time T depends on time and the initial concentration. So if just like with first order reactions, if the initial concentration in K is known, we can find the concentration of A at any given time T at any time. And you only need the concentration of, as I said before, you only need the initial concentration in K to find the concentration of A at time T. Okay. And another thing is that we're lucky here. We only need to be familiar with this form of second integrated rate laws. I'm pretty sure there are other forms of second order integrated rate laws, but this for now is the only form you need to know. So if you noticed that this integrated rate law, this integrated rate law expression is similar to first order reaction, to the first order integrated rate law, where, like before, the concentration of A of a given time T is what we refer to as Y, right? So Y equals mx plus b. So the inverse in the case of second order integrated rate laws. The inverse concentration of a given time t is equal to y. So, and m is equal to k, like last time. T is equal to x, and the inverse, or 1 over the initial concentration, is equal to b, or the y-intercept. Okay. So let's go through an example. So this dimer is so the reaction of butadiene gas C4H6 to yield C8H12 gas is described by the equation 2C4H6, which produces C8H12. So this dimerization reaction is second order. Remember that stoichiometric coefficients do not equal reaction orders. Okay, but nonetheless, this dimerization reaction is second order with a rate constant equal to 5.76 times 10 to the negative 2 inverse molar concentration per molar concentration per minute. So under certain conditions. So if the initial concentration of butadiene is 0.200 molar concentration, what is the concentration after 10 minutes? So here, from this information that we've been given here, we want to apply the second order integrated rate law, right? Because we know that this reaction is second order, right? So 1 over the concentration of A at time t equals kT plus 1 over the initial concentration. So K is equal to 5.76 times 10 to the negative 2 liters per mole per minute. T equals 10 minutes. The initial concentration equals 0.200, and the concentration of A at a given time t is equal to what? So we want to find that. So essentially, it's a very simple step that we have to apply here. All we have to do is just inverse the entire function till you get A of the initial the concentration of A at a given time t, right? As you can see here with this formula here, because what we want to do is isolate for this variable right here, or this symbol right here. We want to isolate for this. We don't want to have that inverse hanging over us. So what we do now that we've inversed the function and we've solved the equation algebraically, it's important that you solve your variables algebra. We want to solve algebraically first before plugging in values, right? So 5.76 times 10 to the negative 2 inverse molar concentration per minute times 10 minutes plus 1 over 0.200 molar concentration. So I've plugged in the values. I found that that these are the resulting values after the first calculation, where we see that we have 3 sig figs here, or yeah, 3 sig figs, as well as no, but yeah, it should be 3 sig figs altogether. I may have made a mistake in representing my sig figs for this calculation, but I still got the correct answer nonetheless, because the answer comes out to approximately 0.18 molar concentration after 10 minutes. Okay? You can just confirm my work on this later if you need to, but I believe that this is the correct answer. Okay? Remember, we want a key idea here is that we want to solve, whenever we're looking for a given variable, we want to solve algebraically first before plugging values. I apologize for cutting out there. What I meant to say is that just upon completing this example, it's important that whenever we're solving for any variables here, we want to solve algebraically first before plugging any values into the formula, before solving for a given symbol or variable. Okay? So moving on to the second example of second order integrated rate laws. when we're using graphs, right, we want to plot out several graphs. So the data below is representative for the same reaction used in example 12.8. So this reaction here, the butadiene gas to yield CH12H12 gas. So we want to prepare and compare two appropriate data plots to identify the reaction as being either first or second order. So to do this, we need to look at the raw data, okay? We want to look at the raw data shown here, and then we want to apply certain functions to it, okay? So so from this, for plot 1, I apply the natural logarithm. Okay, and for the second plot, I apply the inverse, or not inverse, 1 over the concentration of A. Okay, right, and remember that the key feature here to look for is a straight line, right? So for plot 1, when we plot the values of the natural logarithm of the concentration of C4H6 against T, we find that the plot is not linear, meaning it's not a straight line. Therefore, we know this reaction is not second order. However, when we conjure up the second plot, where we apply the reciprocal function 1 over the concentration of A at a given time t versus T, we find that the plot is linear, and therefore we know that this reaction is second order. Okay. However, this is not all the question asks us. So we want to estimate a value for the rate constant. So remember that K is equal to the slope, which is equal to M, right? In this case, it's not negative this time. The slope is not, you don't have a negative applied here. This does not apply, not this time. Okay. K is just equal to the slope, which equals M, which is equal y2 minus y1 over x2 minus x1. And K is equal to 481 in this case, right? This is y2, and this is y1. This is x1, x2. Right? So when you plug in all these values here, you get 6.14 times 10 to the negative 2 inverse molar concentration per second. Okay? Next, let's move on to the half-life of second order reactions. So the half-life for second order reactions is equal to 1 over the rate constant K times the initial concentration. So this is different from first order reactions, where the half-life was previously for first order reactions ln 2 over K, right? So let's consider some important details. So for the half-life for second order reactions, the half-life depends on the initial concentration this time, as well as K. Okay? And unlike first order reactions, the half-life for second order reactions does not remain constant. So the half-life is consistently changes. And in the case of second order reactions, it increases over time for every 50% decrease in the concentration of reactant A. Okay, so let's look at a graph that elucidates on this concept. So the length of the half-life increases with a decreasing concentration. So we can see here, for example, for a second order reaction, that the first half-life is approximately 50 seconds, right? But in the second half-life, we find that it almost takes 100 seconds. T1 half here equals 50 seconds, and the half-life here equals 100 seconds, and then the third half-life is equal to 200 seconds. So we can see that the half-life increases with decreasing concentration for second-order reactions. That's super important to understand. Okay. So with this in mind, let's go through an example for half-life of second-order reactions. So what is the half-life for the butadiene dimerization reaction? So remember the initial values here, where the half-life equals 1 over K times the initial concentration. K is equal to 5.76 times 10 to the negative 2 inverse molar concentration per second. And the initial concentration equals 0.200 molar concentration. So both of them are 3 sig figs. Let's remember that. So just plug the values and play around and see what happens. So we plug in the values. We find that 1 over 5.76 times 10 to the negative 2 times 0.200 molar concentration equals 86.80 minutes, right? But we're looking for the half-life in milliseconds. So we have to do a couple unit conversions. So we convert minutes into seconds, and then we convert seconds into milliseconds, right? And what the answer comes to is approximately 5.21 times 10 to the power of 6 milliseconds. So that's how long it takes for the half-life of a reaction. Okay. Lastly, we have zero-order integrated rate laws. So for a given zero-order reaction where rate equals K times the concentration with reaction order 0, we see that the rate is equal to K, right, for a differential rate expression. So if we integrate this function, we'll get this function here, where the initial concentration, where the concentration of A at any given time t equals negative KT plus the initial concentration. So this equation shows how the concentration of A for any given time t depends on time and the initial concentration and K. So if A and the initial concentration in K is known, we can find the concentration of A at any time. And you only need the initial concentration in K to find the concentration of A. So just like with second order integrated rate laws, you only need to know this form of integrated rate laws. So zero order integrated rate laws. The concentration of A at any given time t equals negative KT plus the initial concentration. And this formula is easy to formula is also easy to memorize and understand because it's also in the form y equals mx plus b. So this is y, this is mx plus b, right? Where y is equal to the concentration of A at any given time t, m equals negative k, right? Or negative k, or negative m equals k, t equals x, and the initial concentration equals b. Okay. So let's look at an example here. So we want to use the data plot here to graphically estimate the zero order rate constant for ammonia decomposition at a tungsten surface. So the decomposition of NH3 on a tungsten surface is a zero order reaction. So from a zero order reaction, we know that this integrated rate law will be the concentration of A of any given time t equals negative KT plus the initial concentration, where K equals negative M. Okay. And K equals negative Y2 over Y2 minus Y1 over X2 minus X1, which is, and once you plug in the values here, so these are the values I estimated. I estimated that Y2 here would be equals Y2 equals 1.5 times 10 to the negative 3 molar concentration. And Y1 equals approximately 2.8 times 10 to the negative 3 molar concentration. Right? X1 equals 0 seconds. X2 equals 1000 seconds. Right? As I've shown here in this plot below. So once you plug in the values here, the final answer comes to 1.3 times 10 to the negative 6 molar concentration per second. So the rate constant has units of molar concentration per second, right? Because this is a zero order rate reaction, right? So it's natural to assume that the rate is equal to the rate constant. Right? Or rate equals K. Okay? Now, this is just the math proofs that, oh, whoops. Now, let's go into the discussion of half-life of zero-order reactions. So, the half-life for zero-order reactions is the half-life is equal to the initial concentration over 2 times the rate constant. So, very important details that we need to know. The half-life for zero-order reactions depends on the initial concentration and K, right? And unlike first-order reactions, the half-life for zero-order reactions doesn't remain constant, unlike first-order reactions, and it's the opposite of second-order reactions, where its behavior is the opposite of that of second-order reactions, where the half-life will decrease over time for every 50% decrease in concentration of the reactant. So if we look at a graph here, the first half-life appears to be about 30 seconds, right? And then by the second half-life, the half-life is about 15 seconds. And then after that, it's about 7.5 seconds for the third half-life, right? So you can see that the length of the half-life decreases with decreasing concentration. This is the opposite of second-order reactions, where the half-life would be increasing, right? So very important details here to keep in mind of. And then this is just the math proof that demonstrates how the half-life is equal to the initial concentration over 2K, over 2 times K, right? So overall, this is a summary of what we covered. Remember that to find the order of remember to verify or find the order of a reaction, you need to determine which plot gives a straight line, right? And and the particular tip for second order reactions, when you're solving for the concentration of A at any given time t, you can simply inverse the whole equation. Okay. And then this is just all the other stuff that we went through today. So just make sure that you guys are familiar with this. I'm pretty sure on an exam you'll actually be given this information. So just make sure that you're well familiarized with it.